Here we go. All right, cool. So we spent a good amount of time talking about like equations of motion. This project is kind of looking at like, at one point we looked at linearizing equations of motion, like what that process was. We had that spring pendulum, kind of kept simplifying it until it turned into like as simple as we could get it. So we'll look at that again, but this time just a pendulum. So coming down, project 3. Is this guy keeping up? Yeah, we'll get there. So I'll do like a little tour through project 3, and then we'll take some measurements, like make a prediction, take a measurement, and figure out what the error was, like how much error we had in our prediction. When engineers say there's error, what does that mean? What? Human error? That's pretty vague. That doesn't seem like an engineer. Result and yeah, so there's some different. Error is always a difference. You take one value, subtract it from another, that's error. Like that's our quantified error. Because in engineering, you're always dealing with like quantifiable things. How much energy, how much power, the force, the stress, like all these things are things that people have like intuitive understandings about. But your job as the engineer, turn it into like some kind of numerical thing. Like how do you measure it? And then the next step is how do you control it? And then somebody else has to deal with like how do you sell it from there? Or maybe that's your job, I don't know. It depends on how many hats your company has you wear. All right, so let's take a look at. So for the pendulum, at least for like a simple pendulum, as in like a point mass attached some distance away from its rotation, we have two options. We can either linearize it, or we can solve like the exact negative g over L times sine theta equation. Which one gives us a more accurate answer? What do you think? Numerical is it always more accurate? Oh yeah, now I'm blocking our screen with a giant chair. Such is life, right? Let's move this over for now. That's better, right? Go back. So what do we think? Is numerical always more accurate? Is there always less error in a numerical? Because that's what, again, accuracy is a measure of error. If error is 0, accuracy, that's as good as best accuracy as you can get. Always better?
I mean, it counts for the non-linearized solutions too, right?
It should converge to it should converge to the linear. Is that what you mean? Or?
Yeah, like it counts for everything, like the linearized solution, just the linear terms.
Okay, yeah. So in terms of like calculating actual acceleration, the nonlinear one is better because it's based on the forces and it is the real acceleration that we'll see. in terms of, there are other errors that come up, and this is part of this project is you figuring out like how do you quantify error between these two different operations, and we'll take a look at that on Monday. We'll like dig deeper into like how to quantify those or like what you notice. But okay, we've got two answers, and we're kind of going to compare the two. So let's go back to a 1 meter pendulum. And let's say our theta 0 is maybe 30 degrees. I think it's 60 to begin with, so let's start with 60. Is this the motion that we would expect from a pendulum? Okay, so if we start, yeah.
One experiencing, like drag force.
Yeah. Yeah, so there's definitely no drag here. How do we know that?
Very consistent.
Consistent? What's consistent though? Like what thing?
Space about.
Okay. Yeah, it has a constant amplitude. Yeah, yeah, so energy has to be conserved. We can transfer it from potential and kinetic, kind of go back and forth, but all right. So now let's look at numerical solution. There's some detail, like if you're interested in like what makes a numerical system work, like how to actually go through it, like that's why the Python code is here. If you're not, if you're like, oh my God, this is all Greek to me, like that's okay. It's just, it's a different way of getting to a solution, at least for now. When you get to computational mechanics, with me, we can go through it in more detail. We're even doing it over the winter if you want like a quick 3-week boot camp of computational mechanics. It's fun. I like it. I think it's fun. More notebooks, more stuff. And let's make sure, yeah, this should be okay. So now, this is our numerical solution. Start at 60, swing down, and then by 4 seconds, we're like on our way back up to 60. Is it the same graph that we just saw? Something's different. Stretched out. What does the stretching out do? What do we call that? And I like to compare it. Like if it's not on the same graph, it's like I don't know what. So there's a blue curve and a red curve. What's the difference between those two curves?
Yeah.
Shifting?
As it goes down, it goes more and more out of sync.
It's what? Oh, more out of sync. Okay. So is that the phase? Like, is it offset?
No. It's like it's like losing, I guess, amplitude. Not amplitude.
Yeah, is the amplitude changing?
No, the wave.
Same amplitude.
The wavelength longer.
Wavelength. Okay, wavelength. What is that one called for this kind of graph? What is it? The period. Yeah, we could call it like the period, or yeah, period is good. Let's do this. Trying to give me, yeah, copy. And paste. What's the period? So this one we said was amplitude, right? Amplitude. Where's the period?
Well, that's the distance between the peaks, right?
Distance between peaks. So like from here to here versus here to there. catching up. So how much error is there between linear and nonlinear? Oh, the live stream is cutting out. That's weird. The audio or the actual live stream? Now this is. So we'll call this like 2 seconds. I'll call this 2.1 seconds. What's the error? Yep. 0.1 seconds. So it's like a 1/10 of a second difference. Whoa. I don't know why this is giving me a hard time. Something like that. Okay. So there's that. We can look at let's get rid of this one. I don't think that's in the original. Let's do this. What are these 3 plots showing? The first one is what we just looked at. What are the next 2? Are they measured in like meters, meter per second? Radians? Okay, yeah. So we've got like degrees, and then radians per second, and then radian per second squared. Okay. What is the same for like that second plot? Do they have the same amplitude? Yeah. It's a little bit different, right? Like here we're saying it's like 2.5 in the linear, it's like 2.5 radians per second. Non-linear, maybe like 2.45 or something, like close, but a small error. And again, we see the same, there's a difference in time period, definitely. And then what about the bottom for acceleration? Something's different, much bigger difference in, yeah, there's a bigger difference in amplitude. We do see both of them are creating like sinusoid, like energy is conserved, so it's going to keep going back and forth. And that one's kind of later. All right, so the things we talked about so far about motion of this pendulum are amplitude and time period. That was really like, what is the time period of a pendulum, of a swinging pendulum? Like what information, what are the things that change the time period? Length of the string, yep. Anything else? Yeah, does the angle matter? Let's try it out, because we can test, at least in our model. We have a simple, pretty simple model, right? It's a simple pendulum, simple model. So we could say, what if it's a 30-degree? What if our initial angle is 30 degrees? So make it half. So now it's swinging at a much smaller angle. Really, most pendulums probably only swing like 10 to 15 degrees. So let's do 10 degrees, just real small. So 10, time period is still 2 seconds, at least from the graph. 0 to 2, and then 2 to 4. So each time period's about 2 seconds. Nonlinear is now also 2-second time periods. Now trying to compare the two results, swinging from 10 to -10. What happened to our blue curve? This is supposed to compare blue and red. It's the same thing, right? Like the two lines are so close that you can't even see the difference. Yeah. So the angle, at least from our result, is that the initial angle doesn't affect the linear, our linear assumption. And if it's a small angle, then there's no difference between linear and nonlinear. There's definitely a difference, like as you get to large angles, there's a difference, but the smaller the angle, the closer everything is. Because now we can see like all three, angular velocity, and angular acceleration is all the same. All right, so we have our first pendulum. It had, oh, go ahead.
How would that possible? That small angle given sine goes to 0.
Oh, sine goes to theta. Like the sine of theta is theta.
Okay.
Yeah. Yeah, the approximation that we're making is that our nonlinear differential equation becomes linear because that sine theta just becomes theta. Yeah, otherwise it'd be pretty boring. Just acceleration 0, so nothing ever happens, or it's constant velocity. How would I figure out, like, what is the equation to find that time period, the 2 seconds? Is it possible to figure that out? Something with velocity, maybe? Okay, but velocity is changing. What's the relation between like time period and frequency? Is there a relationship? T is 1 over F?
Yeah.
I like that. So T. So our frequency, at least like natural frequency, what are the units for that?
Okay, well, frequencies in hertz.
Hertz. What's 1 hertz? What does that mean?
Well, it's 1 over, it's like, well, 10 means negative seconds, but, well, not negative, it's seconds to the first power.
To the -1. Yeah. but what's the numerator? Like what? Yeah.
Like cycles per second?
It could be like cycles, like some kind of, what is the repeating thing that's happening every cycle? So sometimes when we talk about like hertz, it could be revolutions per second. Like it could be like a repeating motion, so swinging left, swinging right, back to right, and now we have one full cycle. So frequency is the cycles per time. Yeah, so if it's a 2-second time period, what is the frequency?
That's 1/2.
1/2, yeah.
So it goes half what it should be per second.
I don't know why my pen is like all over the floor.
It makes sense too that roughly half the size. Well, no, I have to worry about it.
Okay, yeah. What about for like omega? Remember we were doing like differential equations and we had that natural frequency. What is the natural frequency measured in? Is that also like cycles per second?
Spring constant over mass.
Spring constant over mass. Yep. Oh my God, why? My pen is all over the place. Give me 1 second. What, 4? I know there's like 1, 3, 1, 3. All right, let's see if this hurts. It helps. There we go. So in this case, we have like root G over L is kind of like our stiffness per mass, at least for the pendulum. So this is our spring mass. This one's our pendulum. So we could look at like what are the units in here, right? Here is a Newton per meter over kilogram. That one's a little weird. Or we could look over here. This is a meter per second squared divided by meter to the 1/2. That's a little easier. So what happens to the meter per meter? What is that one? Cancels, yeah. And then what about the 1 over second squared to the 1/2? So we have a meter per meter over second. I guess really it's kind of like square root of a meter per meter. But it's unitless. If we just want to go through like unit analysis there. So is this, should this give us 1/2? Let's try it, right? it gave me 3.13. What is that telling me? Nothing? Absolute gibberish. Just yeah.
Saying that your frequency should be one of the or the time. The frequencies.
Okay. Yeah.
That's 3.3. The time should be 1 over that.
Our time period should be, is it 1/3?
It's not.
But it's not 1/3, right? So what are we doing wrong here? All right, so here's a quick lesson on doing math. If there's a sine, a cosine, even an exponential, it's always like radians. It's got to be something unitless, because a cycle is a unit. It's something. There's something in the cycle. Even degrees are a unit. Radians are the only kind of unitless measure of like what fraction of a cycle are you through. So if you've gone through 2 pi radians, you've gone through 1 full cycle. Yeah. Yeah, kind of, yeah, everything. So, and really like every sine, cosine, exponential, logarithms, like they're always expecting a unitless number. If you put units in there, then everything gets a little wacky and you have to keep track of that. So in general, if you see like this cosine omega t, then the number in there is not hertz, it's radians per second. So in order to go through 1 full cycle, we need 2 pi hertz. So in terms of this, omega is 2 pi over t, 2 pi radians per time, which would be 2 times 3.14 over 2 seconds, or pretty much exactly what we just got, right? About 3.1. Pretty darn good. This is all like a verification process. And just like, is our math doing what we expect? Next, we'll do a validation process. Measure something and look at what the error is. Verification, usually error is 0, because you're just like converging to the same thing. Validation, there should be some error, like there should, because in the real world, it's not like a math experiment. If there's 0 error in your validation process, then you've overfit your model, like something happened where things didn't work out. So now let's try that. 2 times np dot pi, or I guess this would be divide by, sorry, what am I doing here? I was trying to find that time period. All right, so there's our frequency, right? 1/2, which is what we had said in hertz. So we can go from like natural frequency, radians per second, into like cycles per second, so hertz. So if we start swinging a pendulum, how do we measure the frequency or the time period? If a pendulum starts swinging, what do you do? How do you measure that? Stopwatch? Yep. And then what are you timing?
How long it takes to go from there to where it started.
Okay, just one time? Do 1 period? Yep.
500
Find an average, yep. What would help with an average? Like, why do an average?
I guess the relates like a month basically every time it goes back and forth.
It's what happens?
It's like how we have to sort of, I think the frequency is changing slightly as it goes on, so it's one average of it.
Oh, you think something is changing as it's swinging? Yep.
In real life, it's getting acted on by drag, friction at its top point, sufficient point, so it will be losing amplitude.
Oh, so really if we measure for longer times, we should see more error. You think so? Oh. I would say the opposite. More measurements is less error, but I don't know. That's my hypothesis. Because so the one thing that I'm thinking about is like start the timer, stop the timer. If I'm trying to start and stop, let's say all I wanted to do was start it and stop it at exactly 2.00 seconds. How well can you stop it? Like
0.00 seconds.
yeah.
I don't think we can do that. Or at least if you definitely let me do it.
You get lucky, right?
Yeah.
So there's some inherent error. So let's call it like 1/10 of a second. So on 2 seconds, if it's 1/10 of a second, that's 5% error. On 20, yeah? Oh, you got 2.01, yeah. So 100th of a second, pretty good. So even 100th of a second, that's like 0.5% error. But if you go to 20 seconds, like measure 10 time periods, now it's still 0.1 second error, but 0.0005%. So your timing error goes down, which is probably bigger. I don't know. Maybe there's other effects that are equally sized. All right, so let's make a prediction. We have a cord that is 118 centimeters, and then a little block of aluminum that's 7.5 centimeters tall. What is the frequency? And I'll write that down. What's the frequency that it's gonna swing at? Let's write it down. New page. So what's our time period? What's our frequency? They're all connected. Like if we know one, we can calculate the others, but that's what we have. I'll go to 9:21. It's still there. It's been a long day, but kind of miss. Haven't been on the spacecraft yet.
what's the time period? So frequency is 2.1, or is it time period? Because before for like 1 meter, for 1 meter it was a 2-second.
All right. Shout it. Do we have any numbers? I know it's Friday afternoon, but we need some kind of number because we're trying to test something. What numbers we got? Did anyone do this? Root G over L? What did you decide on? 2.8. I'll buy it. Radians per second. How about for frequency or time period? I'll take either one. Frequency, time period. Yeah. 19 seconds. Oh wait, 19 hertz? 2 pi times W. So each time, well, so will that mean every cycle is 1/20th of a second? 1/19th, well, 1/19th. I'm just kind of rounding up. What do we think? Yeah. So this is 2.18 seconds. So then what's this one? 1 over 2? 0.4 something? Cycles per second. How do we feel about that? Those numbers? Did anybody, what other time periods did we come up with? Because that's the main thing that's easier to kind of measure here, right? It's hard to watch something and find the frequency. It's surprisingly easy to listen to frequency though. Like a 440 hertz note versus a 445 hertz note, you can actually hear the difference. Because your inner ear is a Fourier transform sort of device. This is pretty amazing. But time period, for slow stuff, it's easier to watch it move, measure time period. Last chance, 2.18. Is that our final answer? That's fine. All right, I'm fine with that. All right, so now take our high-tech measurement device. Who's ready for a timer? We can have multiple timers. Ready to time? This thing. Try this. I don't know how great that, not a great view, but so there. But where do we stop the timer? That's a good question. How do we measure this? What are we doing? Peak to peak. So when I let go, that would be time 0. And there's 1. How many cycles do we want to add? Like, how long do we want to run the timer? If we do 100, we'll be here for 218 seconds.
I think like 5.
5? 5 sounds good. So it'll take 10 point something seconds?
Guess so.
Does that sound good? At least our prediction. That's our best prediction so far. All right, let me know when to go. I'll try not to hit the table.
You can just count down then so we're all the same.
All right. Okay. So I'll go 3, 2, 1, and then I'll say go. So it'll be 3, 2, 1, and then I let go on go. Okay. 3, 2, 1, go. Hit. Sorry. Again. 3, 4, 5. All right.
I
Do it again.
I started really mad. I started really mad. So I got 10 seconds.
10 seconds? All right, let's try again.
Okay, ready?
Okay. 3, 2, 1, go. 1, 2, 3, 4, 5,
Yeah, 10 more seconds.
and
This started a little bit, you know,
11.1.
I was laughing at, and all of them were sitting around like 210, 220.
Okay.
So within the range, like plus or minus, like a tenth of a second.
All right, so let's T measured and then N swings. So what did we get? 10 point what? 6? 10.59 on yours? 10.59 seconds, 5 swings. What was the other one? 11.1? Something? 10.8 seconds for 5 swings. And then we had, what were the other ones? What was yours, Miguel?
I was recording lap times.
Lap times?
1, 2.
Okay.
They all were averaging around like plus or minus like 7
7 what?
like hundredths of a second.
7 hundredths of a second?
Yeah.
So 2.15 plus or minus 7.007?
Yeah.
Or 0.07?
0.007. No, 0.07.
Okay. And then 10.8 divided by 5. 2.16. 10.59 divided by 5. 2.118. So 3 different timers, 3 different, like every measurement has to be different. It's just a fact of life. Like there's gotta be error every time you measure it. Does it account for, is it close enough to our model?
Yes. It's in that range, that 2.1 range.
I mean, it's close to 2.2. Like if we kind of round, if we say we have 2 sig figs, they're all 2.2. Well, except for that first one. That one's 2.1. Round down versus round up, which is our time period 2.2. Okay. How well did we know that length, the length of the pendulum?
Basically, theoretically, they kind of vary between that person. My person really use the full length of the string plus the mass, or if they like stop the midpoint.
Yeah, that's why I was hoping we would get multiple measure. I thought more people would have different approximations for where that center of mass is.
I did both, but my answers were like both kind of the same anyway. So
Both 2.18
no, not that. Right, omega.
omega.
Yeah, I got 2.84 and 2.79, so we go like
Yeah, but yeah, 0.05 times 2 pi, how big is that? And here, we'll go 1. So what did we call this? 1.18? Or what was your L that you used? Was it 1.18?
Let's see, the LI was
2.18 is, yeah, 1.18.
I used yeah, because I had 1.5, so.
Yeah, if you add 0.75, it becomes like 2.2 seconds, 2.25.
And we only had half of 1.75.
Or we could add half of that, right?
0.0375.
And we're 2.21. So somehow we were under measuring at least the prediction there. Oh, we're like out of time. We didn't make the big one. Sorry. Okay, cool. Next time we'll take a look at like running the notebook and kind of talking a little bit more. Sorry I took up too much time with like, because I did want to hang it down the stairs, but maybe we'll like start with that next time, make a prediction, and then we'll start running. Cool, thanks a lot.